Dah mesti dah.
Assalamualaikum warahmatullahi wabarakatuh and good evening everyone. So today we are going to present our group assignment for Scl MTS 3301 and we are from group 2. So my name is Nur Shahida Sufair Abdisaimi and my matrix number is 223392.
My name is Laman Kandan. My matrix number is 223138.
My name is Nur Farhan Hilmi bin Nur Azmi and my metric number is 222621.
My name is Naibati Shawmera binti Isnati and my matrix number is 224086.
Hi, my name is Jehan Hafiza binti Mak Faisal. My matric number is 223246.
Okay, so we're going to proceed with our first question. So for first question, we need to show that function set x is uniformly continuous on interval from 0 to infinity, but we must show that it does not satisfy the Lipschitz condition. So for this question, we are going to start with the first statement, which is the definition for continuous, which is for every epsilon greater than 0, there exists lambda greater than 0 such that the function x minus function y is less than epsilon. Whenever 0 less than x minus y is less than lambda. Okay, so next we are going to show that it is uniformly continuous first. So from this, we use the metric spaces. So we continue the equation, and then we must show that it is less than epsilon. So when we get the less than epsilon, we also continue the equation with for epsilon greater than 0, we choose lambda equal to epsilon with power of 2. So that then we could prove the equation that the function is uniformly continuous on the interval from 0 to infinity. So next. Okay, so next we are going to prove that the equations does not satisfy the Lipschitz continuous. So first we're going to give the definition of Lipschitz continuous. So the function is Lipschitz continuous if there exists a constant such as k, such that the function x1 minus function of x2 is less than k, the constant, in bracket x1 minus x2 for every x1, x2, where x1, x2 is the element of E. Okay, so we first are going to assume that the function is Lipschitz constant. So we try to find the constant. So throughout the equation, we will find that k is greater than 1 over set x. So we know that 1 over set x will approach to infinity, which means k would not be greater than 1 over set x. So these constants not satisfy the inequalities. So we could prove that this function does not satisfy the Lipschitz condition. So I think that's for my part. I will continue with next person.
Okay, for question number 2, we got M1, P1 and M2, P2 as two matrix spaces, and Fm1 approaches to M2. So suppose F is continuous on M1 and F is closed subset of M2, then we need to prove that F inverse F is a closed subset of M1. So from the question we can take that M1, P1 and M2, P2 are matrix spaces, and then we know that M1 approaches to M2 is continuous. So from there we know that F is subset of M2 is closed. So to prove that, we need to let F is continuous on M1. So then we have to let F to be a closed subset of M2. So since F is closed in M2, its complement Ft is open in M2. Since F is continuous, F inverse Fc, which is F complement, is open in M1. But the inverse of F complement is actually equals to bracket F inverse F, the whole bracket of complements, by using the properties of inverse images. Therefore, bracket F inverse F complement is open in M1, which means F inverse F is closed in M1, and we need to prove for the second part, which is suppose F inverse is closed in M1 whenever F is closed in M2. So we need to, can you, Farhan, yeah, we need to show that F is continuous. So to prove that, we need to let G be an open subset of M2, then G complement is closed in M2. So by our hypothesis, F inverse of G complement is close to M1. But we have to use the same property as for the previous one, which is F inverse G complement is actually equals to the whole bracket of N inverse G complement by using the same properties of inverse images. So therefore, F inverse G complement is closed in M1, which means F inverse G is open in M1. Since the pre-image of every open set is open, F is continuous. So the theorem is proved. So
Okay, for question 3, uh, so the question is let M1 row 1 and M2 row 2 be two matrix space and Fm1 to Fm2. Suppose F inverse F is a closed subset of M1 and F is a closed subset of M2. So the question asks to prove that F is continuous on M. So the first one is you let G, you want subset of M2 is an open set. Then it is complement for M1, M2, G is closed. So you assume F inverse F subset M1 is closed, then it is complement in open. So you can see M1 slash F inverse F equal to F inverse M2 slash F and also equal to F inverse G.
Okay, next for question 4. The question is if A is closed subset of a compact matrix space M row, prove that the matrix space A row is also compact. We know that we need to let M1 let M row be a compact matrix space and A be a closed subset of M. So to prove that A is compact, we need to show every open cover of A has a finite subcover. So the first step is let U equal to U alpha, which is alpha element of I, be an open cover of A. Then we let U alpha equal to V alpha that intersect with A. This is because we don't want to have a confuse, so we use V as our what we call, yeah. So A will subset with U union alpha the element of I with V alpha where V alpha open in M. So since A is closed, it is a proof that it is a complement. A complement equal to M so A, that which is it is open in M. So we need to consider the collection that U prime equal to V alpha, alpha element of I, union with A complement. Next. So this is an open cover of M because M equal to A union with A complement that subset with union alpha element of I, V alpha and with union with A complement. And since M row is compact, there exists a finite subcover of U prime, which is M subset of V alpha 1 union with V alpha 2 till V alpha n, that which is union with A complement. Or we can say it is M equal to union I running from 1 to n, that V alpha I union with A complement. So what we need to do is intersect both sides with A. Since A intersect with A complement, we get empty set. Then A subset V alpha 1 union with V alpha 2 until V alpha n. Then we can conclude this is A subset with union I running from 1 to n V alpha I. Since we let U alpha I equal to V alpha I that intersect with A, then A subset with union I running from 1 to n union alpha I. So the conclusion is U alpha 1 till U alpha n is a finite subcover of U alpha, which is alpha, the element of I for A. So since every open cover of A has a finite subcover, then we can prove that A rho is a compact.
So for the last question is, suppose f is a bounded function defined at the closed bounded interval close a to b. If f is Riemann integrable on close a b, prove that for every epsilon is greater than 0, there exists at least one partition C such that epsilon u ft minus L ft is less than epsilon. So for the solution is, if f is integrable on closed interval AB, so we need to let that epsilon is greater than 0. So then there is exist partition P1 and P2 of closed interval A to B. So such that uh, we will have a U f P2 minus integral f is less than epsilon over 2, and integral f minus L f P1 is less than integral over 2. So now we need to let that P is equals to P1 union P2. So then we will have U Ft less than equals to U Ft2 less than integral f plus epsilon over 2 less L Ft1 plus epsilon is less than equals to L Ft plus epsilon. So therefore, it shows that U Ft minus L Ft less than epsilon is proof. So now, if we take that Q is any refinement of P, then we will also have 0 is less than equals to U Sq minus L Sq and less than equals to U Ft minus L Ft. So the so we will have plus the epsilon. So it also shows that U Ft minus L Ft is less than epsilon for any refinement of Q of P.
So that's all from us. Thank you.